Hello guys, welcome back. So let's continue now and add some constraint to the system, and I'm going to copy this node and I want to name the primitives without packing them. So here, create name attribute again, and here we want to turn this off. We can connect the faces here, and then we want to pack it at this level. Okay. So here I want to create the connectivity between the pieces, and right now I'm going to connect the points, the in-between points. Okay. Right now we're connecting the centroid of the geometry, and that's why we're getting this line here. And I want to connect the adjacent pieces from points. And what this does is it's going to connect all the neighboring points and provide a constraint there. So let's name this guy. It's a primitive as constraint name equal, let's call this pin. We're going to use a pin constraint, and type equal all. Okay, let's create a null. And I would CST, let's set this up. So constraint system. We can set it here. And we want a hard constraint relationship. And the name is pin. The path is that. And then the rest length is 0 because the points are, there is no separation or between the points. And let's hide the constraint. I don't want to display that. And let's hit play. Okay, so everything is connected together. And one last thing, I want to set the couple of pieces here to be inactive. So wrangle node I at active equal 1, and then I'm gonna say what's the number of these points, 0 and 1. Okay, so let's copy this, and I want to apply this to 0 and 1, and those guys are inactive. Okay, we're good. Let's go back, and now it's not working. Let's see. Oh, I think, okay. So one more thing I'm gonna set up here is make sure that this box has an active attribute set to 1. So I at active is equal to 1. And let's hit play. Yep. And so we have to make sure that certain attributes are required for the bullet object to work properly. And when we introduce that attribute, it's not it's valid for these guys, but it doesn't exist on this newly emitted object. So I'm simply setting it to active to make sure that that attribute is there. And now we have our pin constraint. As you can see, it hits and stays there. Okay. And so what we want to do is first of all, let me explain one important aspect. Now we did create the constraint between the pieces. Okay, between all the points, and what's gonna happen is it's gonna actually, let me try and draw this. Okay, almost there. Okay, let's fill it with black. And let's paint with white. Okay, pen. Okay, so we have one box. And sorry if I'm not going to be able to draw perfectly because I have two screens and the mapping of the tablet is not perfect by any mean. Okay. Okay, so we have two boxes and we're creating constraints between these points. Okay, so points here, and we're connecting them. When we move this guy, when we apply force to this box, it's gonna move this way. Okay, the anchor point bullet is gonna use is the location of the constraints. So if we give it 4 points that it can rotate on, that it can use as a pivot, it's going to be a very flexible system. If we use the centroid, what's going to happen is bullet is going to join these two. This is the separation. It's going to use the center of this as an anchor. Okay, so this is our anchor point, which means that this edge, this corner here, is going to hit this guy and it's not going to move. But this could be really cool because it's going to create more resistance. If we have points everywhere, it's going to make the system fragile and inflexible to move. So placing the constraint is very, very important when it comes to the freedom, the degrees of freedom the system can have. Okay, the less constraint and the less pivots we provide to bullet, the more rigid the system is going to be, and it's going to have certain limitation where it can move and where it cannot move. So I'm going to explain what I use, and this is part of my system. So we did a test with this guy, and I'm going to change this to connect surface from points, and I'm going to turn on the rest length attributes. I don't want to change these guys at all. I'm going to go back here, and in the rest length I'm going to set it back to 1 so it doesn't change the values. And if we hit play, you see what's happening now. The boxes are sliding on top of each other, but they're still connected. But look at how they're not rotating as a whole group. They're not rotating as a group. They are sliding. That's because they are rotating in the center. They're not rotating based on the anchor point is not in the corners anymore. It's in the center. And so, and that's also because we have an elongated constraint. What I prefer to do is to take this and freeze it into a single point, merge it. So I'm going to use a facet node, and I'm going to separate the primitives and use a primitive node and set this to 0. And now they are all frozen. Let me do a blend shape to show you this. See, this is the original and this is the new position. And let me template this guy. You see where the pivot is now? So that's my connectivity. That's how these guys are linked. And let's go back here and let's hit play. Oh, sorry. The rest length is now 0, so we have to set that back. And look now, it's working. It's very similar to how it was before, okay? But it uses 4 times less constraint in this example. If we had geometry that has more points, it's going to create way more constraints. And this is how we're going to save time, by using constraints that links the centroids, but we freeze them, we scale them down so the anchor point is set up correctly. Okay, and we'll explain this more as we make progress. Now, what we want to do with the feature that I want to show, or that I'm aiming for, is why these boxes are bouncing back? Why are they trying to get back to where they were? Okay, well, if we think about it, at the creation time, the constraints were positioned that way. Okay, they were created in that location. And Bullet is trying to restore that initial state as best as it can. Okay, so what we want to do, if we want to make this feel like there is a metal bending inside, we have to make sure, we have to tell Bullet to ignore that state. Don't go back to your original state. We want to refresh that state with a newly positioned constraints. Okay, so what I'm going to do is I'm gonna import a few things in SOPs and show you what I plan to do. Okay, and imagine, let's show these guys. So I should have left this. So imagine this is our initial frame. Okay, if we take this and feed this as a start frame for Bullet, Bullet is not gonna try and put it back here. It's gonna always try to restore this alignment. Okay, and we only have to tell it internally, don't worry about going back to the original frame. Consider whatever state you're in, your frame, your initial state. And so by doing that, if we stretch it to this frame, it's not going to start bouncing back and go back to the original frame. And so let me import a few things, and this is how I like to do it. I'm going to go to the geometry spreadsheet. I'm going to pin this guy, and let's create a SOP solver. And this is I'm going to use this with a constraint system. And let's dive inside. And I'm going to use an object merge. I know this is weird, but this is how to import the constraint correctly. So we're going to look for relationship, and let's move one frame first. And let's view this node here. Let's go back. I want to move one frame so that the data gets created. Okay, and let's take a look at the geometry spreadsheet. Let's go back in. So under constraints, we are going to find under the constraint network, a geometry data, and that's what we want to import. So I'm gonna drag this guy. Okay, see how this long path is actually pointing to the data, the geometry data inside the SOPs, inside DOBs. Okay, so that's one thing I need, and then I need the RBD object. So this guy, I'm gonna drag and drop this, and that's gonna give me the RBD object. Let's take a look. So that's the geometry, okay, and this is the constraint, the points. I'm gonna copy them. I know this can get a bit confusing, but I'm gonna copy those nodes from inside SOPs, and I'm gonna go up here to DOBs. Let's create a, sorry, I said DOB. I'm gonna go up to the SOP level, and let's create a new geometry node and call this R&D. And let's dive inside and let's paste these guys. Now we have the constraints imported back. Okay, and let's let me disable this. I don't need it anymore. I just used it so you guys can see. And this is our RBD geometry. This is the packed geometry stolen from the RBD system. Okay, as you can see, it's working. Everything is functioning, and this is the constraint. These guys are actually live, and they are getting updated every frame, but just the position, the position is not changing, that's all, which is what bullets expect. So we have all the data there, and what I want to do now is I want to transform these guys with the geometry. Okay, because we talked that if we fed a bullet with the constraint at that position, it will not try to restore itself back. So what I'm going to do is I'm going to use a transform pieces. I'm going to connect this in here and this guy. And if we take a look now, you see that the constraints are now moving. if I do this, we are transforming them, and the way we're doing that is using the name attribute. Okay, and this is how we transform RBD objects, by providing the packed primitives, and anything that has a name attribute, we can transform that. It doesn't have to be the RBD objects. Okay, so these are the constraints, they are transformed. And if we do this inside of DOPS, inside the solver, we can transform their position. And if Bullet likes that, it will try not to go back to that original state. But this is not going to work using just transforming the constraint system, and we need to do this using vex instead, because we need to access something else. We need to access the transform matrix. So if I middle click here, you can see we have a lot of data inside these guys. Okay, we have a lot of attributes inside the Bullet objects, and one of them that we're going to use is called is the prim intrinsic function that's going to return the transform matrix, and this is how this guy is working. So if I do allow editing and dive inside, you can see that it's using this function here that gets the transform matrix. Okay, and this is something that comes with the packed primitives. This is a feature of the packed primitives. This is how we get the transform matrix, and then we can copy that into these guys and transform them. Now, the reason why I want this to be in the points, because I want to invert them later after I do something else to them. So I'm gonna create an attribute wrangle, and I'm gonna connect this in here. And the first thing we're going to use is, let's call this position point number. Okay, the first thing I'm going to need to do is we want to know the point number of this object that has the same name. So each one of these guys has a name attribute. We want to do a lookup, use it to find the object that has that same name, and we want to query an information from it. But before we query any information, we need to know the number of that object. And Vex has a great function to this. We're going to use something called name to points, and this is the perfect use case for it. We simply provide it with the input geometry and the name attribute, and the name attribute is on the constraints. So we have that attribute already. Okay, so we have the name attribute. These guys have a name attribute on them, and we want to say, okay, for this point that has a name X, give me the point number that maps to it from these guys. And so that's what we're storing here, the point number. And then what we need to do is we want to import the matrix. Okay, and for that I'm going to create a 4x4 matrix using this syntax. So for at, I'm going to call this transform matrix, or tran matrix for short, and I'm going to use this function called prim intrinsic, and I'm going to read the matrix from the first input, and the name is called pat full transform. And I'm going to show another example in the next video of this again in details. So we're now importing the matrix from these guys, okay? And we have that data now. All we have to do is we need to multiply P by that matrix. So I'm going to multiply P by that matrix, and look at that. We are now transforming the points with that matrix. Okay, so this is exactly like we did here, but now I have the 4x4 matrix stored. You see it's a 16 float, and I'm going to use that to restore the position later. And we're going to continue in the next video. I want to change one more thing so that I can illustrate this to you guys, and I'm going to show another I'm going to do one more example of this so it's very clear to you guys what's happening here. So thank you for watching, and see you in the next video. Bye bye.